So this morning, I'm looking forward to talking about something that it seems nobody is talking about. Did you know that C++ is unsafe? Oh, okay, I guess you did know that. Yeah, so everybody's talking about that nowadays, and that's terrific for us to, finally start to accept that. I regret to inform you then that I too am going to be talking about how C++ is unsafe. So this morning I'm going to share a little introduction to control flow integrity, looking a little bit at the history of control flow integrity technologies and how they've been developed and improved over time. My goal is to give a broad overview of the landscape, touching on most of the major technologies that are in widespread use today. So we're not going to go into depth into any of them, but we're kind of just going to discuss all the different ways that this problem's been approached for production software. I'm going to focus on what I would call normal-sized computers today. So think cell phones up to big servers. We're going to look at major OSs for 64-bit x86 and ARM. Many of these technologies are applicable to other target platforms. I'm just not an expert in other target platforms, so if you are, you can go and see how these would apply. So we're going to define what control flow integrity is as we go along, but first let's just jump in and write some code. All right, so this will be an interactive exercise just to make sure you're all awake here this morning. I know we all had a great time at the party last night. I'm going to write a little C program. Now I know this is C++ now, not C now, but bear with me. Now I'd like you to please raise one finger when you spot a problem with this code. Okay, so I'd like my program to reach... Wow, all right. Calm down out there. So I want my program to reach some input from the user. So first we'll include the std.io header. And then I heard it's good for programs to have a main function, so I'll give it a main function. So far, so good. Now I need somewhere to store the data that the user is going to type in. So I'll add a buffer where we can store that text. Now, I know it's bad to leave variables uninitialized. Thank you. Yep, I see we saw that. So I'll make sure to initialize the buffer. So now I'm ready to go, and I can call this handy gets function to read whatever the user types in. Okay, yeah, so there's some people do not like that. So as it appears, some of you know, the gets function reads a line of text from standard input into a character buffer. Strangely, tragically, this function does not seem to care how big the buffer is. It only asks us to pass the address of the buffer, not its size. So it's just going to keep writing characters into that buffer as long as the user keeps typing. Now, as long as the user isn't super loquacious and doesn't type too much, we're fine. But if the user types a really long line of text, in this case over 511 characters, then we may be in some trouble. Gets will keep writing right past the end of the buffer, obliviously overwriting whatever might be there in memory after it. Now, we can't really blame gets for this, right? Like, this is actually what it's documented to do. But maybe we could blame the user? Like, we could just put in our program's documentation, like, hey, user, don't, type really long lines of text. Maybe. But I don't really like blaming the user. And even when the user uses our software wrong, it's much better if we handle the error gracefully and let them know that something has gone wrong. Much more importantly, though, when we read from standard input, it may not be from the user typing text into their local console. It might be coming from a file, or perhaps even from an untrusted user over the network. And that, in fact, is how this particular code is used. Or I should say was used. So this is actually real code from a real program, or it's close to the real code. The real source code dates back to the 1980s, so it really looked like this. C looked a little different back then. But this code comes from the 4.3 BSD sources for the finger daemon. That's why I asked you to raise one finger when you spotted the problem. So finger was this tool that would let you connect to a remote computer and query it for information about a user. And so the finger daemon, which handled these remote requests, had this call to gets in it. And as long as the remote user was a polite person and used finger correctly as it was intended to be used, then there was no problem. But if a rude user connected and sent more than 511 characters to the server, then that user could cause the buffer to be overrun, which could result in other memory being corrupted, which could lead to untold mayhem. And surprise, surprise, that is exactly what happened. Otherwise, we would not be looking at this code this morning. So in 1988, this code formed a critical part of the exploit chain used by the Morris worm, which was one of the first successful worms that spread over the early internet. So this is a classic memory safety bug, and worse, it's a remotely exploitable memory safety bug. With this memory safety bug, a remote attacker is able to cause our program to overrun this buffer and overwrite anything that follows it on the stack. And as we know, there are some very important things on the stack. So if we look at the stack when this program is running, we'll find something like this. So the stack goes downward. So at the top, or at the bottom of the stack, but it's at the top memory-wise, we find the data for the function that called our main function, so that would be this start function. And then we have the return address for the main function. And then we have the line buffer, and I've shrunk it down to 16 bytes so it'll fit neatly on the slide. So as long as our user is polite and brief, we don't have a problem. But imagine our user sends a very long string of A's. A is the traditional character for this sort of thing. So first, the gets function will fill the line buffer on the stack. 41 is the ASCII code for the letter A. And then there's still more data. So gets doesn't know that it's filled the buffer, so it keeps writing, corrupting the return address. So now instead of our real return address, we have this value, 41, repeating. The state of our program is hopelessly broken now, though we are likely to keep running just fine until main tries to return. So when main tries to return, it'll pop that corrupted return address off of the stack, and it'll try to transfer control to this address, 41, and so on. And that's probably not a valid address. So the CPU is probably going to raise an exception, not a C++ exception, but a hardware exception. And this will generally result in our program being terminated. The key point here is that by corrupting the return address, an attacker can mess with the control flow of our program. If an attacker corrupts the return address with a nonsense value, like 41 repeated here, then they can cause our program to crash. That's bad, but crashing is always bad, but crashing is actually the least bad thing here. By overwriting the return address with an invalid value, the attacker can make our program crash. But if the attacker overwrites the return address with a valid pointer value that points to actual memory where actual executable code exists, then they can redirect our program to start executing code other than the code it's supposed to be executing. The attacker can effectively hijack execution of our program and make it do whatever they want. So where might the attacker want to redirect control flow to? Well, the most straightforward method of attack here is just for the attacker to bring their own code with them and force our program to start to execute it. We've already seen that the attacker can copy arbitrary bytes into our program. So if the attacker wants, they can take their own program, compile it or assemble it to machine code, and then send that as part of the string that they're going to send to our program. So I've shown that here. The attacker would just append their code and it'll get written onto the stack. Then they'll make sure that in the right place, they'll put the address of that code into their payload so that the return address is now a pointer to their code. So now when the main function returns, it won't cause our program to crash, it'll cause our program to start executing the attacker's code, which is not so great. This sort of vulnerability is called an arbitrary code execution vulnerability because it allows an attacker to hijack control flow and execute arbitrary code inside of our process. When this sort of vulnerability exists in a program accessible over a network, then it's also called a remote code execution vulnerability, or RCE, because it allows an attacker the ability to execute arbitrary code remotely inside of our process. Arbitrary code execution vulnerabilities are among the most severe, most catastrophic classes of software vulnerabilities, because once an attacker achieves arbitrary code execution inside of a process, they can do anything in there. It's as if the attacker got you to run their own program for them in the security context that your program is running in. Great. Not great. So the finger daemon had this exploitable memory safety bug, and when it was exploited, there was extensive damage in the early internet. Now obviously, it's easy to fix the code here, right? We just need to replace the gets with a call to fgets. And that fix was in fact made. Actually, I had some trouble finding the original vulnerable source code to share because almost every archive copy online had this patch already applied. So all right, that's great. We can fix this bug. Problem solved. Except it turned out that tons of programs had these sorts of memory safety bugs that an attacker could exploit to overrun a stack buffer to hijack control flow. And in the years that followed, more and more of these attacks were observed as the internet grew, and as time went on, the complexity of the attacks grew as well. The bug in finger D is obvious when we look at the source code, but in most cases the memory safety bug is far more subtle. So some people started asking, would it be possible to develop a systematic defense against attacks that exploit stack buffer overruns? And that's where control flow integrity starts to take form. Control flow integrity technologies do not fix memory safety bugs. Now that's not to say we shouldn't fix them, just that fixing them is a separate thing. Rather, with control flow integrity technologies, we accept that our program is going to have memory safety bugs in it. We accept that we may not be able to find and fix all of them. We accept that an attacker may be able to find one of these bugs and exploit it to overrun a stack buffer and corrupt a return address. And our first rudimentary goal is just going to be this. Even if an attacker can do all of those things, we want to prevent the attacker from successfully hijacking the control flow of our program. In other words, even if this sort of memory safety bug exists, we do not want it to be usable by an attacker to achieve arbitrary code execution. So let's go. An attacker can overrun a stack buffer, and we can't stop them from corrupting the return address. But maybe we can detect that the return address has been corrupted, potentially by a malicious user. And then maybe we can detect this corruption before we actually execute the return instruction and before we potentially transfer control to the attacker's code. So the first systematic defense that was developed here was the stack canary. Stack canaries were first developed in 1997 in a GCC patch called StackGuard. The idea was developed further over the following years and was gradually adopted by major toolchains in the early 2000s. Visual C++ calls them stack cookies and has had them enabled by default since 2005, so for over 20 years now. And then with GCC and Clang, you still need to opt in at compile time, but both of them support this feature. So the idea of a stack canary is quite simple. So here I have our vulnerable main function which, with its call to gets. We're going to add a global variable. In this case, I've named it stack_check_guard, which is the name that it has in the GCC runtime library. In the Visual C++ runtime library, it's just called security cookie with a bunch of underscores in it. When our program starts up, we'll initialize this global variable with a random number. Now I say we, but really it's just initialized magically for us by the operating system or the runtime library. By the time our code starts running, the random value is just there. Then at the beginning of our vulnerable main function, we're going to add a local variable named canary, and we're going to initialize it with the value of this stack_check_guard global variable. If we look at what the stack looks like, this results in our canary being present on the stack between the return address and our line buffer. We can see that with this arrangement of data, if an attacker overruns the stack buffer and overwrites the return address, then the attacker will also end up overwriting this canary value on the stack. So at the end of our function, just before we return, we'll go ahead and read the value of the canary, and we'll make sure that it has the same value that we wrote there. It should have the same value as the global variable. If it doesn't match, then we know something bad has happened. Now we don't know whether it's been corrupted accidentally or maliciously, but we do know that it's been corrupted somehow. And if the canary's been corrupted, it's possible that the return address has been corrupted. So at this point, we have to figure out what to do, and it turns out the only sensible option is to terminate the program. Now, terminating our program or causing it to crash is not great, but we have no idea what the state of our program is. We know that a memory safety bug of some sort has happened, so we don't even know if it's possible for us to continue executing correctly or even what that would mean. Now, if the return address was corrupted accidentally, then the program is probably going to crash anyway when we return. If the return address was corrupted maliciously, then forcing the program to crash is a whole lot better than executing the attacker's code. This is a trade-off that we're going to make with most of the technologies that we'll look at this morning. We accept that we may have memory safety vulnerabilities in our code, and we just want to blunt the potential impact of these vulnerabilities. Without the stack canary, an attacker is able to achieve arbitrary code execution. With the stack canary, the attacker can still overrun the buffer, but can now only force our program to crash, which makes it a potential denial of service vulnerability. Not ideal, but again, a huge improvement. Now, what I've written here on this slide is conceptual. Throughout this talk, almost all of the code that I'm going to be showing is conceptual. All of this instrumentation code gets added automatically by the compiler, and this is just conceptually what it does. The real-world details may be a little different and will differ across implementations. The important thing for this example is, though, you don't have to write any of this in your own code. The global variable will be defined and initialized by the runtime library, and the compiler will generate all this code to place the canary on the stack at the beginning of the function and then make sure it's valid at the end of the function. This is really cool because in order to get this comprehensive protection for all of our functions, we don't have to change our code at all. We don't have to go and hunt down every potentially vulnerable stack buffer. We just have to enable this compiler feature and recompile our code, and every function is going to be protected. Stack canaries are highly effective because they're simple, their runtime cost is generally very low, and they prevent one of the easiest methods of hijacking control flow. But unfortunately, bad actors are very motivated to break our software. So they didn't just give up, and instead they developed various ways to bypass these canary checks. Now the most straightforward attack vector that attackers have leveraged here is if they can just get the program to give them the canary value. Right? So if they can get the program to give up the canary value somehow, then they can just incorporate that into their payload in the right location so that when it gets overwritten with the original value, and we can't detect the change. There's various kinds of information disclosure vulnerabilities that an attacker could potentially leverage here to do that. And if a program has one memory safety bug, it probably has others. There are some enhancements to stack canaries that have made them a bit harder to thwart and a bit resistant to this. So for example, some implementations will use a per thread canary value instead of a global. So that way an attacker's got to figure out what thread they're actually going to be attacking. And then it's common to XOR the canary value with the stack pointer. So that way it's different when it's written at each location on the stack. I'll leave it to you to go and look into those details if you're interested. The main limitation of stack canaries, though, is that they only protect against this one form of memory safety vulnerability, which is stack buffer overruns. If an attacker can find a different kind of memory safety vulnerability that allows them to overwrite the return address, perhaps without perturbing the canary at all, then the canary won't do anything to stop them. So yeah, those are stack canaries. While there are ways to bypass the canary check, and while now a couple decades later there exist much more sophisticated exploitation techniques that the canaries can't defend against, that doesn't mean that stack canaries are not a useful security feature. To the contrary, they prevent one of the easiest to execute, most straightforward forms of attack, which means that attackers now have to use more complex attacks. So this makes their job harder. It makes development of reliable exploits more expensive, and that in and of itself is a win. Stack canaries are also inexpensive at runtime, so the cost of this protection in runtime overhead is very low, which is also a win. So stack canaries were only the first technology that became widely adopted here. There were several other technologies that were also developed and deployed around the same time in the early 2000s, and we'll look very briefly at two of them, one software technology and one hardware technology. So in our stack buffer overrun example, I sort of brushed over one tiny but important detail. Our attacker copies their code onto our stack and then sets the return address to point to it. But how did they know where that is? After all, in a 32-bit process, let alone a 64-bit process, the address space is quite big and the stack is just very small. And the simple answer is, at the time, the operating system would just always allocate the stack at the same address. Actually, the operating system generally preferred to allocate at the same address everything, each time the program was run. So to try and load the program itself at a consistent address and to do its best to load shared libraries at consistent addresses and the stack, and even within the heap, allocations would often be, very consistent. Why? Well, that's just the easiest thing to do, and it's the fastest thing to do. And until you have to start worrying about attacks like this, you're not going to try and do, something more complicated. Anyway, while it's the easiest thing for the OS to do, it also makes things way easier for attackers to execute all sorts of attacks, since they can know with high certainty how things are going to be laid out in memory in the process that they're targeting. It's like they have a map of where everything is going to be. So to make things harder for attackers to find things in a running process, operating systems started implementing address space layout randomization, or ASLR, and it's exactly what its name indicates. So instead of allocating everything at fixed locations or relatively predictable locations, the OS basically randomizes them each time the program is run. So most major OSs added support for ASLR in the early 2000s, around the same time that stack canaries were introduced. When ASLR is used, if an attacker wants to execute a successful remote code execution attack, they'll generally have to find some way to get the program to give them some information about how things are laid out in memory. So sometimes there's weaknesses or limitations in the ASLR implementation that may allow an attacker to discover this information. Or sometimes they may be able to rely on some information disclosure bug, where the program prints a pointer into a log, and then now they can derive from that, information about the layout of the program. So ASLR doesn't completely solve any problem. It just adds extra hurdles that an attacker will have to clear in order to achieve a successful exploit. So the second technology, or the third technology, I guess, that came about in the early 2000s was non-executable memory. So in our stack overrun example that we've been looking at, the attacker takes their own code that they want to execute, they copy it into our process, onto our thread stack, and then they get our program to execute it. So what if the CPU just didn't let you do that? Now the x86 family of CPUs has supported marking regions of memory as non-writable or read-only all the way since virtual memory support was first added to the 286 in 1982. If you mark a region of memory as non-writable, then when your program goes to try to write to it, the CPU will raise an exception, and that'll generally result in your program being terminated. It'd be nice if we could also mark a region of memory as being non-executable. Then when the OS goes to allocate a stack for the thread, it can tell the CPU, hey, this region of memory where the stack is should never contain executable code, and so we should never attempt to execute code from it. So with non-executable memory, if a program tries to return to or call to or jump to or transfer control in any way to an address that's in a non-executable region of memory, the CPU just won't let that control transfer take place. It'll raise an exception and it'll terminate our program. Non-executable memory was not a new idea, but it was a relatively late addition to x86, and x86 CPUs have only supported it since like 2003 to 2004. There's a bunch of different names for this feature, but they all mean the same thing, and there's probably other names elsewhere. Now, the way I describe this feature, it might sound like we're going to mark some regions of memory, like the stack, as non-executable. But in practice, it's more like the reverse. So the default will generally be that we allocate almost all memory as non-executable. And then in the few places where we actually load executable code into our program, we'll mark that memory as executable. For the most part, this will just be parts of our program binaries that get mapped into memory, plus maybe some JITted code. So now if we come back to our example program, an attacker may still be able to exploit the stack buffer overrun. They may be able to bypass the stack canary somehow. They may be able to copy their code onto the stack. They may be able to bypass ASLR, and they may be able to figure out the address at which their code is going to be located in memory on the stack. And they may be able to overwrite the return address with that address. But now when the CPU goes to execute the return instruction and it tries to start executing the attacker's code, it'll see that the memory region is non-executable, it'll raise an exception, and the program will be terminated. So success, problem solved. I hope you enjoyed the talk. I'll take your questions. No. Or maybe not. Okay, so non-executable memory was a huge security improvement, and when combined with stack canaries and ASLR, these three technologies together made it much harder to successfully hijack control flow. But as we noted previously, bad actors are highly motivated to break the programs that they're attacking. So as these increasingly advanced defensive technologies were gradually adopted, attackers became increasingly sophisticated in their attack methods. So now that we can mark memory as being non-executable, an attacker can't bring their own code into our process for us to execute, which is great. Unfortunately, our process is already full of code. It sort of has to be, because if it wasn't, it wouldn't be able to do anything. Notably, we probably have a bunch of shared libraries loaded, and one of those is probably the C runtime library, and that C runtime has all sorts of very useful generic functions in it, like the system function, for example. So the system function lets our program run some other program, and this seems like a very useful thing for a runtime library to have, but it also seems like the sort of thing that an attacker might find very useful. Like if they could call this system function and have it run a program for them, that might be nice. So what attackers started doing is instead of bringing their own code with them, they started using code that was already available in the process, and which was already marked as executable. The most basic form of attack here is called return to libc. And with the return to libc attack, basically the attacker will overwrite the return address with the address of some function inside of the C library or some other library or the program itself. This way, when the function returns, instead of returning to its caller, it'll jump to the start of that library function, like the system function, almost as if the system function had been called. Okay, so the attacker can hijack control flow and can get our program to call the system function for them. That's bad. But the system function requires a parameter, and if the attacker wants to do something useful with this function, they're going to need to figure out how to set that parameter value to a value that's useful to them. On 32-bit x86, this is generally very easy because in most calling conventions, arguments are passed on the stack. So the attacker just needs to put their command string on the stack and then put that pointer to that string in the right location on the stack, and then the system function will find it. But on 64-bit x86 and many other architectures, in the predominant calling conventions, the first few arguments are passed in registers. So for example, when you call the system function on 64-bit x86 Linux, the address of the command string has to be placed in the RDI register. Now, thankfully, while it's possible to exploit memory safety bugs to overwrite memory, registers aren't memory. You can't take the address of a register or overrun a buffer to overwrite a value in a register. So even if our attacker can overwrite arbitrary memory, they can't overwrite register values. At least, not directly. So with the return to libc attack, the attacker overwrites the return address with the address of a function that already exists in our program. Our attacker, however, is not limited to functions. Our attacker can overwrite the return address with the address of any instruction, even if it's in the middle of a function. So as an example, if somewhere in our program we have the instruction sequence pop RDI ret, then an attacker could overwrite the return address with the address of this pop RDI instruction and then put the value of their choice just above it on the stack. So then when our function returns, it'll transfer control to this pop RDI instruction, which will pop the attacker's value off of the stack into the RDI register, and then the following return will be executed. The attacker can then make sure that they've carefully constructed the stack that they have full control over, so that that ret will then jump to the start of the system function. By chaining these two operations together, the attacker can load the address of their command string into the RDI register and then call the system function to execute that command. Little instruction sequences like this have been dubbed gadgets, and an attack that involves chaining these gadgets together has been rather cheekily called return-oriented programming, or ROP. Most unfortunately for us, a lot of research has been done here, and it turns out that most programs contain enough gadgets that return-oriented programming is Turing complete. So an attacker can generally transform any program into a chain of gadgets, which unfortunately means for us that an attacker can achieve arbitrary code execution within our process even without being able to execute any code of their own. Okay, so next we're going to move on to a couple of modern technologies that have been developed over the last decade or so, but before that I want to refine our threat model a little bit. We set out at the beginning of this talk with a goal. And that goal was that even if an attacker can overrun a buffer on the stack, we want to prevent that attacker from being able to hijack control flow. Stack canaries, address space layout randomization, and non-executable memory all make it harder for an attacker to hijack control flow by overrunning a stack buffer. But these are all speed bumps of a sort, and as we saw, there's ways to bypass them. As attacks get more sophisticated, we also need to become more sophisticated with our defenses. And so over the last decade, two major new technologies have been introduced that bring pretty substantially stronger defenses here. So far we've been looking at the case where an attacker overruns a buffer on the stack. Now that is, of course, a memory safety bug, but it's not the only kind of memory safety bug. Memory safety bugs come in all sorts of fun flavors. Some are a little bad, others are catastrophically bad. The worst memory safety bugs are those that allow an attacker to perform arbitrary reads or writes of data within our process address space. So with an arbitrary read vulnerability, an attacker can read the value of any byte in the address space of our process. And then with an arbitrary write vulnerability, an attacker can write a value of their choosing to any location in the address space of our process. Now, when I describe that, both of those might seem extremely unlikely, but in fact they are more common than we would like. So here, for example, we have a very simple class. It has a std vector as a data member, and it has a member function that lets a caller update the value at a particular index. Now there is nothing wrong with this function, but if there's any code path through our program where the index and the value are controllable by the user without proper sanitization, then this function can potentially become part of an arbitrary write vulnerability. With a carefully calculated out-of-range index, an attacker can cause this function to write their value to any location in memory. So going forward, we're going to consider a broadened threat model. Even if an attacker can exploit arbitrary read and write vulnerabilities and alter the return address, we want to prevent the attacker from successfully hijacking control flow. That is, even if an attacker has the worst possible memory safety bugs at their disposal, we want to prevent them from being able to tamper with the control flow of our program as it exists, like in the code that we wrote. By assuming that the attacker has the worst possible vulnerabilities at their disposal, we ensure that the defensive techniques that we develop will be robust regardless of how severe the actual memory safety vulnerabilities are. So we'll add one caveat here, and that is we're going to say the attacker can't change memory protections. So an attacker can't make a non-writable page of memory writable or a non-executable page of memory executable. This is a fairly reasonable caveat because in order to change memory permissions, a program has to make a syscall like to mprotect or virtual protect. Code that makes these syscalls is relatively rare, and it's rare enough that it's actually tractable for us to audit the code that makes these calls to make sure that those APIs are used in a safe way. So this is our goal. It's ambitious. Let's see how close we can get to it. If we want an even stronger defense against control flow hijacking, perhaps it's time to reconsider some fundamental parts of computer architecture. So let's rethink the stack. If we look at the thread stack, it looks like something like this. First, we've got A's return address, the address that A will return control to when it's finished. Then we've got A's local state. Then A calls B, and so we'll have B's return address and B's local state, and so on. So we have one stack, but we use it to store two completely different kinds of data. We use it to store our control flow state, that is our return addresses, and we use it to store our function local state, our local variables and other such things. Now this seems natural to us because, of course, this is how things have been done effectively since the beginning of structured programming. It's easy to understand why it made sense to combine these things, a long time ago when, silicon was, gates and so forth were very expensive. But, there's nothing that says these have to be on the same stack. What if we split the data up and we had two stacks for each thread? We'll have one stack which contains only our control flow state, that is our return addresses, and we'll have a different stack that will contain our function local state, our local variables, and other such things. Now, if we do this, we can see that obviously a stack buffer overrun could never result in a return address being overwritten, right? Because the stack buffer is going to be over there on the local stack, but the return address is going to be over here on the control flow stack in some completely unrelated region of memory. So that's awesome. But there's actually a second, less obvious benefit of doing this. Local variables need to be generally accessible. What I mean is that local variables are, from our perspective as C++ programmers, just C++ objects. We need to be able to read from them and write to them and take their address just like we do any other C++ objects. But the same is not true for return addresses. The only two instructions that should ever be touching return addresses are call and ret instructions. And we can maybe put a little asterisk on that because there are exceptions, like exceptions. But those exceptions truly are exceptions, and maybe we can deal with those as special cases. So if we split our stack in two and store our control flow state separately from our normal program data, maybe we can make it so that only call and ret instructions can touch that control flow stack. So just like we added the ability to mark memory regions as non-executable, maybe we can add the ability to mark a memory region as only touchable by call and ret instructions. If we can do that, then we can make it completely impossible for an attacker to hijack control flow by overwriting a return address via any memory safety bug at all, because we would make it impossible for them to overwrite the return address. So in 2020, Intel introduced a new set of features to the x86 architecture, which they called Control Flow Enforcement Technology, or CET. And one of the features added by CET is called the shadow stack, which gives us something kind of like this split stacks approach. When we enable shadow stacks, each thread still has a normal thread stack that contains both return addresses and function local state. It's exactly the same as the thread stack before. There's no changes there. However, each thread also now has a second stack, which is called the shadow stack, which contains only the return addresses. So the call instruction is going to be updated so that it now pushes the return address onto both the thread stack and the shadow stack. Then the ret instruction is going to pop the return address off of both stacks. It's going to compare the values, and if they're the same, then the return is executed because it knows, okay, this is the correct return address. If they're not the same, then something has gone wrong. The return address on the thread stack has probably been corrupted, and in this case, the CPU will raise an exception which will terminate the program. The shadow stack is specially protected, and it's not generally accessible, so only call and ret instructions can read and write to it. There's also a few other special purpose instructions for implementing things like exception handling and stack unwinding. But yeah, so that's basically it. Shadow stacks are surprisingly simple. Maybe the first reaction we might have, though, is this does seem a bit more complicated than it needs to be. Why not just go with the split stacks approach? That certainly seems much cleaner. And the answer is, perhaps unsurprisingly, compatibility. The behavior of the call instruction, where it pushes the return address onto the thread stack, has been part of the x86 architecture from the very beginning, and most notably, major software ABIs, including the Windows ABI and the System 5 ABI, depend on this behavior. Basically, all software in existence would be broken if this was changed. So while this approach is not as architecturally clean as having two completely separate stacks, it does maintain legacy compatibility, and it's just as effective from a security perspective. Yeah?
Does it cost a register to point to the shadow stack?
Does it cost a register to point to the shadow stack? Yes, but it's a new register, so it's not reusing an existing register.
Okay.
Yes. And actually, shadow stacks can be implemented in software on some architectures like ARM, and like Clang has a feature to do that. And when they do that, it does actually take one of the general purpose registers. But for the Intel implementation, there's like a completely different shadow stack register.
There's a small performance win to capturing a stack trace. It becomes a mem copy if you have a shadow stack.
Yes, it could lead to faster, some things being faster and easier, because walking a stack like requires looking at metadata to figure out where the next return address is if you don't have pointers to the next frame. So shadow stacks completely prevent control flow hijacking via malicious modification of the return address. With them, we completely achieve the goal that we set out for ourselves. So that's super awesome. Intel and AMD have both supported shadow stacks in their hardware since 2020. Windows has supported shadow stacks since the first hardware was available. Linux support came a fair bit later. It's like in the Linux kernel 6.6, I believe, and then there's some more recent version of glibc that's required in order to set everything up right. So that's shadow stacks. Shadow stacks are the gold standard here. Super advancement in security on x86. Yeah.
So if you have this technology, you probably give up on the other older technology, right? You don't need that anymore.
Absolutely. So once we are all running on machines that support this, we do not need stack canaries at all. Absolutely. But for the moment, if you're running on machines that may not have this feature still, like older user machines or what have you, then you probably want both. So that you get the improved protection on machines that have it and stack canaries for the machines that don't.
Yeah, just run on new machines.
Yeah, that's. I would love it if all of our customers would just buy new hardware.
Yeah, buy
absolutely.
more processors.
Buy more Intel processors.
That's right. Yeah, but we should move on from Intel. We've given Intel too much coverage here. So what about ARM? ARM has also introduced a new technology for protecting return addresses, but their technology is completely different. So let's take a look at pointer authentication, or PAC. The first thing we have to note is that the call and ret instructions work differently on ARM than on x86. Actually, how many people program for ARM and are familiar with the ARM architecture? Okay, so we'll do a little crash course here. So on x86, the call instruction pushes the return address onto the stack and then transfers control to the call target. And the ret instruction pops the return address back off of the stack and then transfers control to that address. On ARM, well, first off, there's no call instruction. ARM has a different instruction called BL, which stands for branch with link, and it's used for direct calls, and then there's a BLR instruction that's used for indirect calls. Whereas on x86, the call instruction pushes the return address onto the stack. The ARM BL instruction takes the return address and it places it in a register called the link register. It's also X30. Then it transfers control to the call target. Then, since the call instruction doesn't push the return address onto the stack, the ret instruction doesn't pop it off the stack either. Instead, it just takes a register as an operand, and it transfers control to the address in that register. Most of the time, we'll specify the link register as the operand, because that's just how it's done. And in the assembly language, the link register is just the default if you don't specify a register. So when the compiler generates code for a function, it needs to generate instructions in the function prolog that explicitly copy the return address from the link register to the stack. And then it needs to generate instructions in the function epilogue that explicitly copy it back off of the stack so that we can return through it. So here on the left, I've got a main function. It just calls another function f, and then it returns 0 to its caller. And on the right, we can see the assembly for this function. So I'll just walk through it quickly. The str instruction, store register, pushes the return address from the link register onto the stack. Don't worry about all the silly punctuation. It is not important for this talk. The BL instruction calls f. The move instruction then places the value 0 in the right register for the return value. And then the LDR instruction, load register, pops the return address back off of the stack and into the link register. So then finally we can return to our caller. Easy peasy. So now all of you are ARM assembly experts, and you can go and add that to your LinkedIn profile. The important thing to note is that on x86, pushing and popping the return address onto the stack is automatic and implicit in the way that call and ret instructions work. On ARM, it's explicit, so if a function needs to save its return address, it has to do it itself. Shadow stacks made sense on x86, where the call instruction already pushed the return address onto one stack, Why not push it onto 2? But on ARM, it's not so obvious that that idea fits in with the fundamental design of the architecture. It's not clear that it makes sense to change the behavior of the BL and RET instructions, and we can't reasonably change the STR and LDR instructions because they're just general purpose store and load instructions. There's nothing in the instruction that says, oh, this is a return address that I'm pushing onto the stack. We have a unique opportunity here, though. Because our function explicitly writes its return address onto the stack, it has the opportunity of doing something with the return address before it writes it to memory. So, what to do? Well, let's take a step back. Imagine we have some data, any data, maybe it's an email or a network packet or a file or whatever, and we want to ensure that if the data is tampered with in some way, we'll be able to tell. Any ideas how we do this?
Check some hashes.
Hashes? Well, you could recompute a hash, though. An attacker could compute the right hash. Signing. There we go. Yeah, we'd sign it cryptographically. So that's what ARM did with pointers. ARM pointer authentication was added in ARM v8.3, which was published in 2016, 2017, and Apple's A12 CPU was the first hardware to include it in 2018. So pointer authentication provides hardware support for cryptographically signing pointers and then for cryptographically authenticating those signatures. Pointer authentication is also called PAC, P-A-C, as the signature that it produces is called a pointer authentication code. So what we're going to do is at the beginning of our function, before we write the return address onto the stack, we'll add this PAC instruction. It will cryptographically sign the return address in the link register. Then, at the end of the function, after we read the return address back off of the stack, but before we transfer control through it, we'll add this auth instruction, short for authenticate. It'll recompute the signature for the pointer in the link register. If the signature does not match, then we know that the pointer was tampered with or corrupted, and so an exception can be raised and the program can be terminated. Okay, so the first question we're going to have to solve is, where are we going to store this signature? And to answer that, I'll ask you, the audience, a question. If we're running on a 64-bit CPU, on a 64-bit OS, and our program is a 64-bit program, and it has 64-bit pointers, how big is our address space?
48 bits.
48 bits. Oh, that's a great answer. Yeah. The best answer is it depends. But yeah, 48 bits. So for our purposes here at the moment, we'll say 48 bits. So we have a 64-bit pointer, and we only use 48 bits of it to store the address, which means we have 16 unused bits just sitting there. They're always 0. Actually, not quite, because on ARM, bit 55 has special meaning. But OK, fine. We have 15 unused bits. Let's put the signature there. So our pointer will have 48 address bits, this special bit 55, and then a 15-bit signature called the pointer authentication code. So the way this will work is as follows. So we have here on the left our pointer, which for our use case here is the return address. And we feed it into this PAC instruction. So the PAC instruction also takes 2 other operands. So first it takes the key to be used for signing. Now we don't want there to be any possibility for the attacker to read this key, so our program doesn't actually have the key. There's a secret register inside of the CPU that the kernel can write the key to, but our program can't read it. There's no way for us to get access to it, so there's no way for an attacker to exfiltrate it unless they compromise the kernel, which is a way bigger task. Our program will just refer to this key by an identifier, and the CPU supports up to 4 keys. So there's 2 for signing instruction pointers and then 2 for signing data pointers. So we'll just say which of those keys we want to use. Then the PAC instruction also takes a 64-bit modifier value, which can be any 64-bit value we like. So it takes these 3 inputs and it uses a cryptographic algorithm implemented in hardware, so it's very fast, to produce a signature for our pointer. Then it stores the signature in the unused bits of our pointer, and we get a signed pointer. We can then take our signed pointer and write it to memory. Then at the end of our function, we'll read the signed pointer back from memory, and at this point, we need to authenticate the signature to make sure it's still valid and the pointer wasn't tampered with. And to do this, we'll use an auth instruction. So like the PAC instruction, it takes 3 inputs. This time we give it the signed pointer, and then we have to give it the same key and the same modifier value that we used when we originally signed the pointer. The auth instruction will recompute the signature. If it's valid, then it'll just remove the signature from the pointer. It'll leave us with the original pointer value. and then we can pass that to the ret instruction and we'll transfer control. Everything is just as it was. If the signature is invalid, it might be nice if the auth instruction would just like raise an exception right then, but for reasons it doesn't in the initial implementation, there was then like an amendment to ARM where it does, but I'll describe the original one. Instead, what it does is it sets the high order bits to our pointer to an invalid state. So like at least one of the bits will be 1 and the other one will be 0. So that way, when we attempt to dereference it or transfer control through it, then an exception will occur. So the auth instruction won't raise an exception, but the ret instruction that follows it will. If we come back to our example function, then we can fill in the last details. At the beginning of our function, we'll use this packIB instruction. So this will sign the return address in register x30, which is the link register. It's going to use the IB key, which is like the B instruction key. And then we're going to pick the stack pointer as the modifier value. Now we could use 0 or some constant modifier, but if we did so, then whenever we sign a particular return address, it'll always have the same signature. By using the stack pointer as an input to the signing algorithm, like we ensure that we get a different signature for each different location in memory where we're going to store the signed pointer. We picked the stack pointer for this purpose because like it's a little different at each place in the stack, and it's also should be the same in both the function prologue and epilogue. So then at the end of our function, after we load the signed return address back from the stack, we'll use the authIB instruction. This will authenticate the return address in x30, again using that same key and using the stack pointer as our modifier value. There's one final implementation detail I want to note. Obviously, one disadvantage of pointer authentication is that our compiler has to add these instructions to the beginning and end of all of our functions, which means we have to recompile our program. And because these are new instructions, like if we do this, then our program won't run on older CPUs because like the older CPUs don't know that these, what these instructions are. They'll find them and they'll raise an illegal instruction exception. So in order to make pointer authentication partially backwards compatible, ARM included several special purpose instructions that are used just for signing and authentication of return addresses. So there's a couple of special instructions, packIBSP and autIBSP. These have exactly the same behavior as the instructions on the prior slide. They're just encoded in a way that old CPUs will treat them as no-ops and new CPUs will do the right thing. So that then is pointer authentication in a nutshell. At this point, pointer authentication is available in most relatively recent 64-bit ARM devices, since it's been around since 2017, 2018. Major OSs support it, including Linux, Android, iOS, Mac OS. I could not find information online about the current state of Windows on ARM.
How is this better? Yeah.
But yeah.
That's exactly the slide I was going to
Yeah,
ask.
so now that we've looked at these two approaches, like we can compare the protection offered by shadow stacks and pointer authentication. So for shadow stacks, it's easy. Like as we said before, an attacker cannot successfully hijack control flow by corrupting any return address, period. That's great protection. Pointer authentication also offers great protection, but it's not quite as great. So with pointer authentication, an attacker can modify a return address in memory as long as their substitute return address is properly signed. Now with stack canaries, we discussed how an attacker might leverage some sort of read vulnerability to exfiltrate the canary value. Similarly, with pointer authentication, an attacker could leverage a read vulnerability to exfiltrate, some signed return address that's on the stack. But crucially, an attacker is limited to real return addresses that our program has already signed and written to the stack at some point. So in general, ROP is not possible, and attacks here would be extremely narrowly constrained. One other weakness with pointer authentication is an attacker can just try to guess the signature. So when we have a 15-bit pack, an attacker has like a 1 in 32,000 chance of guessing the right signature value, right? Those are not good odds if you're an attacker. But unfortunately, pointer authentication is not the only thing that these higher order bits may be used for. So notably, ARM also supports memory tagging, which reserves the higher order 8 bits to store a memory tag. And now ARM also supports the larger address spaces, up to 52 bits. Actually, when I was researching this talk, I learned that in ARM 9.4, they increased that to 56 bits. And when you add like all these things up, I do not know how they all fit together. Maybe they found a way to fit, more bits into 64 bits. Anyway, if you enable memory tagging and use the enlarged 52-bit address space, that only leaves 3 bits to store the pack. which gives an attacker a 1 in 8 chance of guessing the right signature, and that's potentially more palatable odds. Now, this is the worst case. Enlarged address spaces are not in widespread use, at least not yet. But even if we ignore the worst case, like shadow stacks are clearly better from a protection perspective. So wouldn't it be nice, like, if ARM would just support them? And the good news on that is in ARM v9.4 announced in 2022, they add a new feature called guarded control stack, and it works more or less the same way as CET shadow stacks, so I'm not going to talk about them because I'd just be repeating myself. Like, there's a bunch of ARM-specific stuff, but like from a security perspective, it's basically the same. To the best of my knowledge, there's no ARM 9.4 CPUs in production yet, but someday, in the not-too-distant future, we can look forward to guarded control stacks being available, and then we'll have shadow stacks everywhere, which will be awesome, and we'll have completely solved the problem.
Sure.
Yeah.
For all.
Or we'll have completely solved the first half of the problem, because there is, unfortunately, another half of this problem. For every return that we execute, there must have been a corresponding call. So if we look at the execution of functions in our program, we can represent the call graph as, well, a graph. In this graph, each function is a node, and then between those nodes we have directed edges. So when one function calls another function, this forms a forward edge in the graph, and then when a function returns to its caller, this forms a backward edge in the graph. So in short, a call instruction, or a BL instruction on ARM, forms a forward edge in the graph, and then a ret instruction forms a backward edge. Stack canaries, shadow stacks, and return address signing all protect against attempts to hijack control flow by corrupting return addresses. So all of these control flow technologies provide what's called backward edge control flow integrity. What about the forward edges in this control flow graph? Can calls be similarly attacked? And if so, should we be developing technologies to defend against those attacks? So every return is the same. Each function has the return address of its caller stored somewhere, either on the stack or in ARM, in the link register. The target of a return instruction is always dynamic. It depends not on the function that we're currently in, but on what function called that function. Whereas every return is the same, there are different kinds of calls. So a call can either be direct or indirect. With a direct call, the source code says exactly what function is being called, right? So in this example, we have two functions, f and g, where f calls g. This is a direct call because we can look at the source code for f and we can see, oh yeah, it's calling g. And when this gets compiled, that call gets baked into the machine code. So for example, on x86, we might have a call g instruction. In order for an attacker to hijack control flow of a direct call, the attacker would have to modify the machine code of our program, but since the executable code is generally stored in a region of memory that's protected as non-writable, like, the attacker can't do that. So direct calls, we'll say, cannot be hijacked. With an indirect call, the source code does not specify a specific target for the call. Rather, there's a layer of indirection between the caller and callee, and the basic mechanism of indirection here is a function pointer. So in this example, we have a function pointer fp, and f calls the function pointed to by this function pointer. A function pointer may be located in memory that's writable, for example, in a global variable or in a struct or class or on the stack. And if a function pointer is located in writable memory, then it's at least potentially possible that an attacker might be able to tamper with it, replacing it with a pointer of their choosing. If the attacker can then get the program to call through that function pointer, then they can hijack control flow. So with return address corruption, we saw how an attacker might find gadgets, each ending in a ret instruction, and then they might be able to chain these gadgets together using return-oriented programming, or ROP, to achieve arbitrary code execution. There's a similar pattern that can be used with function pointers called jump-oriented programming, or JOP, where an attacker takes gadgets that end in an indirect branch or call instruction, and they chain these together to achieve arbitrary code execution. Job attacks are way harder to put together, but now that return-oriented programming is being thwarted much more effectively, they become a more appealing option for attackers to pursue. So the answer to our question is yes, we're going to need technologies to help defend against forward edge control flow attacks as well. So this will bring us to our final definition of what control flow integrity is. even if an attacker can exploit arbitrary read-write vulnerabilities, and thus can read any byte from the address space of our process, and can modify or corrupt any byte, we want to prevent the attacker from successfully hijacking control flow. As before, we assume that the attacker cannot change memory permissions. So effectively, our earlier definitions of control flow integrity focus solely on return addresses. But now we'll assume that the attacker can corrupt any state, including return addresses, but also now including function pointers, v-pointers, and any other state in our program. We already solved the problem for return addresses, so now we'll look at the solutions that have been developed for function pointers. Production-grade technologies here are fairly recent. Relatively speaking, all of them have been introduced within the last 12, 13 years or so. I'm going to introduce two pure software-based protective technologies, Microsoft's Control Flow Guard and then Clang Control Flow Integrity. And then we'll look at a couple of hardware-assisted protective technologies. Before we jump in, though, I also want to very quickly note that everything I'm about to say about function pointers also applies to polymorphic C++ classes and virtual functions. I'm going to focus on function pointers. They're just simpler to talk about, but just know that both the problems and the solutions that we're going to look at apply for virtual functions as well, with some little differences here and there.
Are virtual function tables often stored in non-writable memory?
Virtual function tables should always be stored in non-writable memory. However, the v-pointer inside of the object can be corrupted to point somewhere else, and so an attacker might be able to fabricate their own v-table that you end up pointing to. Cool. So the first technology we're going to look at here is Microsoft's Control Flow Guard, or CFG, which was first released in 2014. To start off, we'll consider a very simple question. What values can a function pointer have? On a 64-bit platform, a function pointer is just an 8-byte number, effectively, so it can have any value that can be represented in 8 bytes. But for our purposes, we can group the possible values into two broad categories. Either a function pointer points to a function, or it doesn't. Now, there's a lot of possible values in that second category, right? Like it could be a null pointer, or it could be an invalid address that won't even pass address translation, or maybe it points to data, or it points into the middle of some function. Who knows? The only important thing is that it doesn't point at a function. So our function pointer may point to a function, or it may not. So for control flow integrity purposes, we can start then by saying that it's only valid to call through a function pointer if it points to a function. I know, that seems obvious, but this is an important observation. After all, there's trillions of bytes in our address space, but there's probably at most only a few million functions. And it turns out we can refine this even further. We can actually say it's only valid to call through a function pointer if it points to a function whose address is taken somewhere in the program. So if we have a function and we only ever call it directly, and we never take its address anywhere in the program, then that means we never legitimately form a function pointer to it, and at runtime, it should never be called indirectly through a function pointer. So this idea leads us to the basic principle of Microsoft's Control Flow Guard. Before we make an indirect call, we want to check where the function pointer points. If the function pointer points to an address taken function, then we'll make the call. If the function pointer points anywhere else, we're going to terminate the program. So here on the left-hand side again, I have a function f. It takes a function pointer fp as a parameter, and it just executes a call through it. With Control Flow Guard, the compiler is going to instrument this call to perform this check. It checks, does this pointer point to a valid call target? And if it does, it's going to make the call through the function pointer. If it does not, then it's going to terminate the program. Now again, this is all conceptual, it's actually just inline checks, but we'll show it this way for simplicity. So this is simple enough. It just leaves us with the challenge of implementing this isValidCallTarget target function. The first thing we have to do is identify all the valid call targets. So we start in the source code where somewhere we take the address of a function f. The compiler will see this. The compiler sees everything. And it'll put metadata in the object file that says f is a valid indirect call target. The linker will then take this metadata from all the object files that it gets, and it'll merge it into one big list for the whole executable binary that it produces. Then at runtime, as the loader loads each binary into our process, it'll read this metadata and merge it into one big lookup table. So yeah, we'll just create one big lookup table. So we can write a first conceptual implementation of isValidCallTarget like this. We imagine we have a big lookup table containing one bool for every address in our process's address space. So it needs to have 2 to the 47th elements in it, because that's the size of the user mode address space on x64. If an address is a valid call target, then the loader will set its value in this lookup table to be true. If it's not a valid call target, then it'll be false. So then in isValidCallTarget, all we have to do is look up the entry for the target address in this lookup table and see if it's true or false. And like this conceptually is actually how control flow guard works. Now, okay, I admit there's some problems with this conceptual implementation. Or there's like one big problem, right? The good news is this valid call targets array has one element for every byte in our address space. Each element is a bool, so it takes up 1 byte. So this array takes up 128 terabytes of memory. You see, this is good news because it means it fits perfectly into our process's address space. The bad news is it doesn't leave room for anything else. So that might be a little problem. But we can make a couple optimizations here to reduce its size. So first, obviously, we don't need a whole byte to store this information, so we can use a bitmap. For reasons beyond the scope of this talk, we need 2 bits per address, but still it shrinks the size by a factor of 4, so that's great. Second, we can align all functions that are address taken, so all valid call targets, on 16-byte boundaries. Now this requires some collusion between the compiler and the operating system. So the compiler and linker have to ensure that all address taken functions are 16-byte aligned, and then the OS will assume this is the case and it'll track valid call target state only for every 16th byte. So this obviously shrinks the size by another factor of 16. So together, these shrink the size from 128 terabytes to 2 terabytes, which is a lot smaller. And the table actually does take up that much space of our address space. But it doesn't take anywhere near that amount of memory. Because note that in our 128 terabyte address space, only a very tiny fraction of that space contains any executable code at all. So the vast majority of this table is just zeros. So with the way the control flow guard works is it reserves the whole 2 terabytes of address space for the table, so it can't, it won't be used for other purposes. But it only needs to commit the parts of that table that actually contain at least one valid call target, where there's at least one 1 in there. So it needs to allocate memory only for a very small fraction of this table. So as an example of this, I use this VMMap tool to visualize the virtual address space for Explorer.exe running on my laptop. I sorted the address space regions by size, and by far the largest region was the CFG bitmap. So this is a screenshot from that tool. We can see the size of the bitmap is 2 terabytes, as we expect, but only about 67 megabytes is actually committed. So the table is only using 67 megabytes of overhead. Additionally, we can see in this screenshot that the region is shareable. So as an additional optimization, the operating system will share parts of this bitmap across multiple processes in the system wherever possible. So for example, there's one DLL, NTDLL, which gets loaded in every single process. It's the same DLL that gets loaded in every process. It's loaded from the same file. It gets loaded at the same location. It gets mapped in the same way. And so it has the same set of valid call targets in every single process. So the CFG bitmap for that part of the process should be the same in every single process. The OS can thus share the memory used by those parts of the bitmap across all processes in the system. So that's control flow guard in a nutshell. Control flow guard restricts indirect calls so they can only be made to address taken functions. The protection here is what we'll call coarse-grained protection, because any address taken function is potentially callable through any function pointer. Now this might sound a bit weak, right? Like after all, an attacker could overwrite a function pointer with the address of any other address taken function, and there's probably a lot of those. But it does defend against jump-oriented programming, where an attacker might try to call into the middle of a function, into a gadget. And that in and of itself is a substantial protection. It's a huge improvement in security over not having any protection at all. So with that, I'm going to set control flow guard aside for just a moment. We're going to look at Clang CFI, and then when we've looked at how that works, we'll compare and contrast the two approaches to understand their design trade-offs and their strengths and weaknesses. So Clang control flow integrity, or Clang CFI, is an umbrella term for a set of compiler-based security technologies related to control flow integrity in the Clang compiler. There's actually a number of really cool technologies in here. I'm only going to focus on its indirect call protection, since that's what this talk is about. And you can go and check out the documentation if you're interested in the other cool stuff in there. Clang CFI provides forward edge control flow integrity that protects against control flow hijacking attacks where a function pointer is corrupted. At the most basic conceptual level, it's very similar to Microsoft's control flow guard. With Clang CFI, at each place in the source code where you make an indirect call, the compiler will insert instrumentation that checks, does this function pointer point to a valid indirect call target? If the answer is yes, it'll make the call. If the answer is no, the program is terminated. That, however, is where the similarities end. Clang CFI is implemented in a completely different way. So when we looked at control flow guard, we saw that a function is a valid indirect call target if and only if its address is taken somewhere in the program. The same is true with Clang CFI. However, Clang CFI does something quite interesting here. So here on the left, I have a small example. We declare a function g, and then inside of our function f, we take the address of g and we assign it to a function pointer. So g is address taken. When we enable Clang CFI, the compiler transforms this code into the code on the right. Clang is going to create a thunk for g, which for example purposes I've just named g thunk, though in reality it has an unwieldy name that's special to the compiler. This thunk consists of a single instruction that just jumps to the start of g. Then inside of f, when we take the address of g, instead of giving us the actual address of g, Clang is going to give us the address of this thunk. Clang performs this transformation every time we take the address of a function, which means that the only function pointers we should ever have in our program point to these compiler-generated thunks. And this gives us something very useful. During compilation, we're going to end up with all these thunks. I'm not very creative with my function naming, but for example, if we have functions a, b, c, and d, and all of them are address taken, then we're going to end up with 4 thunks. Each of these thunks consists of a single jump instruction. This jump instruction happens to be 5 bytes in length. And this is a very interesting thing, right? Because in general, a function can be any arbitrary length, right? Maybe function A does nothing and it's just like a single ret instruction, and it's only 1 byte long. Maybe function B has some gigantic algorithm in it and it occupies megabytes of memory. The point is we don't know. But every one of these thunks is exactly 5 bytes in length. Every one of these thunks is thus exactly the same size. And if we have some things in memory, and they're all the same size, and if we line them all up in memory one after the next, we can effectively form an array out of them. So here on the right side, I've taken our 5-byte thunks, and I've added 3 bytes of padding to each, so that each element is 8 bytes. I hear powers of 2 are really great. And then I've lined them all up so they form an array. The compiler people will call this a jump table, but I think we can call it an array if we want. So we'll give this array a name. I've called it valid call targets because that's the name we had in the previous section. And so with this, let's recap what we have here. The only address taken functions in our program are these thunks. These thunks are thus the only valid indirect call targets in our program. We've just lined all these thunks up in memory into an array. When we make an indirect call through a function pointer, we want to know, does this function pointer point to a valid indirect call target? Now that we have this array of thunks, this question is the same as, does this function pointer point to an element in this array of thunks? If it does, then it's a valid call target. If it doesn't, then it's not. So we can easily then re-implement our isValidCallTarget function for Clang CFI. So we have our valid call targets array, which is our array of thunks, and we need to check 2 things. One, does the function pointer point somewhere within the bounds of this array? So is it greater than or equal to the start of the array and less than the end of the array? And 2, if so, does the function pointer point to an actual element in that array and not some random byte of that inside of that element? And that's it. As I've written the code here, this is 3 conditional tests, but in fact, this can be transformed into a very efficient single conditional test and branch. If you are interested in how to do that, I would just encourage you to try Clang CFI out and take a look at the code it generates. It's quite clever. Yeah?
So if you have suppose you have a lot of functions, right? So for understanding that the function pointer is valid or not, this is good enough. But when the translation happens from function pointer to the thunk, right? So you still need to know exactly where in that array your thunk belongs to, so that you can translate to that. So you need a linear search there, right?
You don't. Yeah. So you don't actually need any search because you have a pointer into this array, And you will actually just transfer control to that because that's the jump instruction, and it's just going to then jump to the right call target.
Makes sense. Thank you.
So a cool feature of the Clang CFI design is that it doesn't require any help from the OS. There's no global bitmap of valid call targets that has to be maintained. The compiler just builds up this list of valid call targets itself and produces this array of thunks. This design is also cool because it enables us to refine our validity check. Imagine that we have a program and we have all these functions in it. All of them have their addresses taken somewhere, so they're all valid call targets. However, at the C++ language level, they're not all valid call targets for every indirect call site. When we make an indirect call through a function pointer, that function pointer has a type, and that type had better match the type of the function being called. Now the compiler does its best to enforce this by requiring you to use a very ugly cast in order to cast from one function pointer type to another. But even if you put one of those dangerous looking casts in, you're still not allowed to actually call a function indirectly through a function pointer of a different type. It's not allowed, the behavior is undefined. So for example, if we have this fp1 here, which is a pointer to a function with no parameters, when we ask, does it point to a valid call target, ideally, we only want the answer to be yes if it points to A or B, because those have the same type. Similarly, if we have fp2, which is a pointer to a function with one int parameter, ideally, the only valid call targets should be C, D, and E, because those have the same type. Now with control flow guard, where we used a bitmap to determine whether an address was a valid indirect call target or not, we were effectively limited to just one bit of information for each address. It either is or it isn't. And we said that that was a coarse-grained check. But with Clang CFI, where we're using an array of thunks, we have more flexibility. And that flexibility allows for much finer-grained call target validity checking. Instead of having one big array with all of our thunks in it, we can actually have one array for each function type. So if we have these 7 functions, we'd have one array with the thunks for A and B in it, one array with the thunks for C, D, and E in it, and then a third array for F and G. Then at each call site, the compiler will say, okay, so this function pointer is to a function that takes one int parameter, so I'll perform the validity check using that array of thunks. So at no additional cost, this substantially improves security because it substantially reduces the set of valid call targets for each particular call site. So that's Clang CFI's indirect call checking in a nutshell. And now that we've looked at both of these, we can compare their designs and see what trade-offs were made and what their pros and cons are. So the first thing we should look at, of course, is the protection they offer. After all, these are first and foremost features for improving the security of our software. Both protect against jump-oriented programming and gadget-style attacks, where the attacker might corrupt a function pointer with the address of some gadget in memory. They're different, though, in how much they restrict the attacker, right? Control flow guard only has coarse-grained validity checking, so an attacker can, in theory, overwrite a function pointer with the address of any other address-taken function in the program. Clang CFI has finer-grained checking, so an attacker is more limited. If an attacker is going to overwrite a function pointer, then they'll need to pick an address-taken function of the same type. So while both technologies offer substantial protection here, Clang CFI is clearly better because the set of valid call targets at each indirect call site is substantially smaller. Control flow guard requires cooperation between the toolchain and the operating system. Clang CFI, on the other hand, is completely toolchain based, so it doesn't require any help from the OS at runtime. I'm sure you can imagine why OS independence is of great value to the people working on Clang, and maybe of somewhat less value to the people working on Visual C++ and Windows. Control flow guard works with basically any build. You can even enable it in debug builds, and the toolchain will produce the appropriate metadata. When we looked at Clang CFI and I said the compiler produces these arrays of thunks, I skipped over a tiny little thing there. In ordinary C++ compilation, where the compiler only sees one source file at a time, no instance of the compiler actually knows the full set of thunks, no matter, or it doesn't even know how many of them there will be. Only the linker knows that when it sees all of the inputs into the binary all at once. Thus, Clang CFI requires that we enable link time optimization so that when the optimizer runs at link time, it can produce those arrays of thunks. We should, of course, be using link time optimization. It makes our programs faster. But if we aren't, then we have to enable it if we want to use Clang CFI. And it does mean that we can't use it in debug builds.
Why is it independent of link time optimization? Just another linker option.
Because the compiler is going to bake into the code that it generates the size of the table. I agree. I think there might be ways that this could be implemented without relying on link time optimization. One other challenge, though, is if you have like static libraries that don't have metadata, like in them, you might end up with function pointers, crossing the boundaries that then end up unchecked, or you fail checks because of that. Control flow guard has this neat feature that it's incrementally adoptable. So if you have a large application, you can gradually enable control flow guard for parts of it, and then work over time to get it turned on for everything. It has support for backwards compatibility with old libraries and DLLs that weren't built with CFG. Obviously, in that case, its protections are weakened, but like partial protection is still better than no protection. With Clang CFI, you basically have to enable it for everything in your binary all together, all at once, because this array of thunks must be complete. So there's no like easy transition option where you can enable CFI checks for some of your code and not other parts of your code. Now I have to put an asterisk on that because Clang CFI does support a blacklist or an exclusion list, so you can exclude certain files or functions or types from having CFI checks added. But this can be a bit tedious to fine-tune, I can say from experience. With control flow guard, indirect calls to dynamically loaded DLLs are easy. Right? So this bitmap used to represent call target validity is global for the whole process. So the information for all the DLLs just gets merged together, and checking of cross-DLL calls just works. This is extremely important on Windows, where it's very common to make indirect calls to dynamically loaded DLLs, especially because of the way COM works. With Clang CFI, though, our arrays of thunks are specific to one binary. If we want to make a call to a function in a different binary that we've dynamically loaded, we're going to need to have some special way to handle that. Clang CFI has a few options here to help with that, but they all impose either additional runtime cost or reduced protection. Control flow guard can work with any language and toolchain. So for example, if you build a new DLL using Rust and you want to make sure that your calls between your mostly C++ program and your Rust DLL are checked, then it just works. Microsoft implemented support for CFG in LLVM, and it's supported for both C and C++ code and for Rust. Other languages, even JIT compilers at runtime, can provide information to the OS about valid indirect call targets. So generally, interoperation is super straightforward. Clang CFI is Clang specific and C++ specific. There's no real interop story there. Now you might ask why you need this sort of protection for Rust code, which is safe. And the answer is, first and foremost, to protect it from all the potentially vulnerable, unsafe C++ code in the process. Finally, just from personal experience, the coarse grain checking that control flow guard does generally just works. The finer grain checking that Clang CFI does should just work, as long as you're not doing anything funny like casting function pointers. Unfortunately, it turns out there is an awful lot of code out there that casts function pointers. So depending on your particular code base and dependencies, it can be a bit of a chore to adopt. Now my point with this comparison is not to declare a winner or say that one is better than the other. If we look solely at the protection provided, yes, Clang CFI is better. But as with almost everything, there's trade-offs and there's pros and cons to both approaches. And it's interesting to see what might have led to the different design choices here.
James?
Yeah?
Is there a perf comparison between these? What's the perf story?
Let's talk about that at the very end.
Okay.
Yeah. Yeah.
Shouldn't CFI be able to statically identify you've cast between these two function pointer types and combine them into a single type?
Shouldn't it be able to detect that? In the general case, probably not. It depends. You shouldn't be doing it anyway. So the Clang builder is going to say, don't do that, But potentially, I guess it would be my answer. Yeah.
So what I was going to say is what I sometimes see is casting function pointers to a single function pointer type and then casting back.
That will work fine. Yes, as long as you cast back, it's the right.
But your static analysis is going to totally break down on that because everything has to get merged.
Yeah, then everything gets merged into one big chunk.
Well, yeah, and then you get limited protection like Control Flow Guard has. I'm going to run to the end of the talk, and then we'll do Q&A at the end because I don't want to run out of time here. So we are getting close to the end of the talk. Microsoft Control Flow Guard and Clang CFI are both pure software defenses. They work on existing hardware and don't really depend on any special hardware-specific features to work. While we looked at them in the context of 64-bit x86, the techniques are not x86 specific in any way. Pure software techniques are nice, obviously, because they work on existing hardware, and adding new features to hardware is expensive, and there's a very long lead time between when the new features are added to hardware and when they're widely usable. But pure software technologies here, will have a higher performance impact. So for both Control Flow Guard and Clang CFI, we saw the compiler needs to generate additional instructions to perform this call target validity check. And while it does, it reduces those to the minimum it can, like the CPU still has to execute those instructions, and that execution isn't free. So what if we could get the CPU to help us out here? Intel and ARM have both added instruction set extensions that provide hardware support for coarse-grained forward-edge CFI, similar to the protection that Control Flow Guard offers. Intel's implementation is called IBT, or Indirect Branch Tracking. It's part of CET, which is the control flow enforcement technology that we mentioned earlier. IBT was introduced in Tiger Lake in 2020, and to the best of my knowledge, AMD has not implemented this yet in their chips. ARM has a very similar implementation called BTI, or Branch Target Identifier, and it was added in ARM v8.5 in 2019 with CPUs coming out just a little later. So we'll look briefly at Intel Indirect Branch Tracking. It's very simple. It adds a new instruction called NBranch. There's two versions of it, one for 32-bit code and one for 64-bit code. These instructions are designed to be put at the top of functions, so they'll be the first instruction in a function. When IBT is not enabled for a program, NBranch is a no-op. Old CPUs will also treat this instruction as a no-op, so it's backward compatible. When IBT is enabled for a program, NBranch actually is also a no-op. So NBranch is always a no-op. It's very simple. What could be simpler than doing nothing? But okay, so it has to be doing something somewhere else. So when IBT is enabled, it's actually the call and jump instructions that are modified. So with IBT, whenever a program makes an indirect call or jump, the next instruction executed must be an NBranch. So the idea here is the compiler will put this NBranch instruction at the top of every indirectly callable function. When the CPU executes an indirect call instruction, they'll check, is the next instruction, is that first instruction that this function pointer is pointing to, an NBranch instruction? If it is, then the CPU allows the call and execution continues. If it isn't, then the CPU raises an exception and our program can be terminated. Effectively, we get something similar to the coarse-grained protection offered by Control Flow Guard, but implemented in hardware without having to perform the checks in software or maintain this bitmap. So it should be much more efficient. ARM's branch target identifier feature is largely the same, except instead of NBranch, the instruction is called BTI, and then of course instead of the call instruction, it's the BLR instruction that's updated, and so on. So yeah, hardware support for coarse-grained protection here is quite straightforward. But we already saw that Clang CFI, with its finer-grained protection, offered better security improvements. And so it would be kind of nice if we could get that finer-grained protection with the help from hardware to hopefully reduce the runtime cost that we have with the software checks. And for that, we come back to the end of the talk. At the end of the talk, looking at pointer authentication again. So in the first half of this talk, I feel like pointer authentication was kind of a letdown. Like, it seems super cool. At least applying cryptography for protecting pointer values in memory is cool to me. But while pointer authentication offered very good protection for return addresses on the stack, it wasn't quite as good as shadow stacks, and so it feels kind of over-engineered and overcomplicated. Except for one little thing. Pointer authentication can be used to protect any pointer, not just return addresses. So if we look back at our diagram of how pointer authentication works, we can think about how this might be usable to protect function pointers. So first we have our three inputs. Our pointer was a return address in the first half of the talk, but in this case, now it'll be our function pointer. The cryptographic key, which will be provisioned by the operating system for us to use, is the same as we were using for return addresses. And then the 64-bit modifier is the third input, and we'll come back to that. So we feed these three inputs into the pack instruction, and it'll give us a signed function pointer that we can write safely to memory. Then later, when we want to use that signed function pointer to make a call through it, we'll read it back from memory and then feed it, along with the same key and the same modifier, into the authentication instruction. It'll authenticate the signature, and it'll either give us back the original function pointer, which we can successfully call through, or it'll give us a tainted pointer that will cause an exception to be raised when we call through it. Now, if we ignore the modifier, then we could pretty easily imagine using pointer authentication to implement coarse-grained indirect call target validity checking. Whenever we write a function pointer to memory, we sign it first, and then whenever we read a function pointer back from memory to make a call, we authenticate the signature. The modifier in this case can just be 0 or some other constant value. If we do this, then an attacker would be able to override a signed function pointer with another validly signed function pointer, but only with another validly signed function pointer. As our program executes, hopefully it's only going to sign function pointers that point to valid indirect call targets. And since an attacker can only overwrite a signed function pointer with another valid one, that means an attacker can only redirect a call to another valid indirect call target. So from a security perspective, we would get something very similar to what Control Flow Guard offers. But we have this modifier, which can be any arbitrary 64-bit value. The only rule is it has to be the same value during both signing and authentication. So if we sign a function pointer when we first take the address of a function, and we authenticate the function pointer when we're going to make a call through it, one thing that we know must be the same at both of those places is the type, right? The type of the function has to match the type of the function pointer through which it's called. So what we can do is we can use the type as the modifier. Now obviously we can't fit a C++ type into a 64-bit integer directly, but what we can do is we can hash the type and produce a 64-bit hash code, and we'll use that as the modifier. And with that one little trick, we get finer grained type-based protection similar to what Clang CFI provides. Now there's some pros and cons to this approach. On the pro side, it works across shared library boundaries, just like Control Flow Guard did. But it also requires rebuilding every single piece of code in your process to use PAC, because function pointers can be passed across shared library boundaries, and both sides of the interface had better agree on whether those pointers are signed or not. But if all your code is built with PAC enabled, this technique is really cool. We get fine-grained forward-edge control flow integrity with hardware support that should make it far more efficient than software-based solutions like Clang CFI. So there's been a lot of research here. As of today, I believe the only major platform where this technique is used is Apple's platforms. Apple has been working on this for some time. So as I mentioned earlier, pointer authentication was first added to the A12 CPU in 2018. I believe Apple has had PAC enabled for their system software for a while, but then it was only last year that they made it available for you to use starting in iOS and macOS 26. There's a new ABI that you have to target when building your application called ARM64E, and I think the E stands for enhanced. But yeah, if there's people with iPhones in here, I'm sure there's a lot of pointers being signed and authenticated in this room right now. And with that, we've reached the end of the talk. I hope that you found this an interesting tour of some of the modern technologies being used today to defend against control flow hijacking. I hope there was something new in here for everybody. I know I covered a lot of materials, so a lot of it was necessarily high level and conceptual. There's detailed information about all these technologies available online, like tons of documentation, tech docs, articles, academic papers. And at this point, I'm happy to take any questions you may have. But I'm going to... And I'll start with Ben, because it's the question that I knew I was going to get.
What's the perf story?
Yeah, what's the perf story? So I didn't say anything about performance. And the answer is, it depends. So some of these techniques are free, like non-executable memory and address-based layout randomization. You just get them, and there's no real cost to them. Stack canaries have basically negligible overhead. Shadow stacks have effectively negligible overhead. There's some memory overhead for the extra stack, but generally it's very low because it's only storing the return addresses, and whereas functions on the normal stack may have a bunch of data that makes the stack big, it's really rare for the shadow stack to be more than a page or two in memory. Pointer authentication is structured in such a way, obviously cryptographic operations are not necessarily cheap. My understanding is that the PAC and authentication instructions are generally 5-cycle latency. However, you don't actually need the result of the PAC instruction that you do at the beginning of a function until the end of the function when you go to authenticate it. So basically the chip just goes off and starts doing that in the background. And the whole thing is designed to so that the chip can easily speculate and have very, very low performance impact for those. Control Flow Guard and Clang CFI can have a several percentage point performance hit in your application. I can't give an exact number because it depends entirely on how many how frequent your indirect calls are in your program. You could imagine a worst case where you're always making indirect calls to different functions in a tight loop. and then like it might have like huge overhead. If you don't do any indirect calls, then it's going to have no overhead. So yeah, it just depends. The important thing with performance is that most major software platforms, including like very performance critical software platforms, are using this today. So it's been used in the Mac and iOS, pointer authentication has been used in the Mac and iOS kernels for some time. The Windows kernel has been using Control Flow Guard for over a decade. Almost all of Microsoft software is built with Control Flow Guard enabled. Clang CFI is used like by Chrome, I think, on Linux. So like there's a lot of performance critical software that's also security critical, and like this is fast enough to justify its security value is, I think, the way I would suggest looking at it. Yeah.
So when I look at the GCC page on hardening and all this stuff,
Mm-hmm.
there's a half dozen, maybe more things, including I think it's FCF protection, and they claim that does both ROP and job.
Yes.
And is there somewhere that maps what you've talked about to the flags?
No, but you can look up, in the documentation. So GCC, my understanding, they don't have anything similar to Clang CFI,
Right.
where it does the fine grain checking, but they do have the FCF protection, which has, it basically puts in both the, I think it does the shadow stack thing, and then it also does the end branch instructions or the BTI instructions on ARM. So it does both, and then
Okay.
there's sub options you can do to select which ones you want. I admit I'm not I haven't used GCC in ages, but
Okay.
yeah.
Fair enough.
Yeah.
So the last part with ARM, and you're guarding indirect jumps across a shared boundary,
Mm-hmm.
right? So both sides have to agree on what the type ID number is for all sides, right?
Yes, so it has to be
So-
part of the ABI, like the encoding technique for the types has to be part of the ABI.
Right. So I mean, if they're different compilers, or hopefully Clang keeps it stable between versions, you have to be careful in the shared.
Yes. So in this case, for Apple, they've just declared this is the ABI, and the compiler has to match it. So if another compiler wanted to go and add support for this, they would have to match. And I think they've documented it fairly well. I'll take one more question, and then any other questions after the end.
Alright, so for that PAC, right, the authentication part, the ARM authentication, so you have 3 bits worth of places to store the signs, right? And you are taking 3 different input channels, putting them through the cryptographic changes to generate one of the 3 bits in a way that makes it like the sign, right? So can someone not see the probable input and without even going through the whole hassle of the cryptographic signing, not predict what is going to be the sign, because it's only 8 different options? And
Yes, so in that worst case where you enable the larger 52-bit address space and memory tagging, then you only get 3 bits. If you don't have both of those enabled, then you get 15 bits. So the number of bits you get varies, and then ARM 48 bits is just a typical, but 39 bits is also common. So you may have even more bits available. But yes, certainly in that worst case where there's only 3 bits available to you, that's those are good odds if you're an attacker, right? To I've got a 1 in 8 chance of being able to hijack control flow. Certainly better than 1 in 32,000.
yeah, makes sense. Thanks.
So cool. Yeah, if you've got any more questions, happy to chat during the break, and thanks for coming.